Oil and the time it takes to separate after being mixed with water. How does the amount of saturated fat of different oils affect the time it takes for it to separate after being mixed with water? You've most likely noticed that water and oil are unable to mix. The purpose of this experiment is to use what we know about the chemical natures of these two substances and deepen our understanding of how the amount of saturated fat in oil affects its bond with water. For the experiment, the independent variable is the type of oil used, the dependent variable was the time measured in seconds, and the constants were the amount of water, the amount of oil, temperature, and the way that the substances are being mixed. It is hypothesized that the oil with the highest concentration of saturated fat will separate from water the quickest. This means that as the percentage of saturated fat increases, the time it would take for the oil to separate from the water would decrease. Water is a polar liquid, meaning that there's a separation in polar charges, so one side is positive while the other is negative, and the molecules bond by shared electrons. Oil is nonpolar, meaning that its electrons are evenly distributed throughout the molecule. The term like dissolves like is used to show that polar mixes with polar, while nonpolar mixes with nonpolar. Due to this, the oil molecules are unable to bond with the water molecules, since the water molecules are attracted to themselves, and the oil molecules are also attracted to themselves, which causes them to separate. Polar molecules are attracted to each other through their hydrogen bonds, while nonpolar molecules are attracted through the London dispersion force. This is a temporary force that technically happens between all molecules, but tends to be weaker with nonpolar molecules. A saturated fat is a long molecule consisting of mostly single bonds. Oils and fats are made of esters composed of 3 fatty acid units linked to glycerol, called triglycerides. Saturated fat consists of nonpolar molecules. An unsaturated fat is a molecule that includes a double bond. And then these are the structures of 3 oils that were used in the experiment. And olive oil has 2 grams of saturated fat per tablespoon. Canola oil has 1 gram of saturated fat per tablespoon, and sunflower oil has 1.5 grams of saturated fat per tablespoon. So for the experiment, you want to measure out 150 milliliters of water and put a drop of food coloring into it, and then measure out 150 milliliters of the oil and put it into the same container, and then wait until the oil and water are separated and then draw a line between them, and this line will serve as a guide. And then you put on a lid and shake the container for about 15 seconds until the color of the liquid is all one color. And then as soon as you put the container down, immediately start your timer and observe. And since the water is colored, you'll know when the two substances are completely separated. And then you can also use that line that you drew to help you. And once the oil and water have completely separated, you stop the timer and record your results. And then repeat steps 3 to 5 4 more times with the same oil and record your time for each trial. And then repeat all these same steps with the other oils until you've completed all of your trials. And then these are pictures taken during the experiment, and you can see the blue water at the bottom and each of the different oils on top. And then this table includes all the times from the trials as well as all of the average times for each of the oils. And then this graph allows you to see the data and the patterns that they create. So each line is each oil, and you can just see how the times kind of fluctuate. And then this bar graph makes it easier to see how each of the individual trials compare with one another. The hypothesis predicting that the oil with a higher concentration of saturated fat would separate from water the quickest was proven correct by the data collected. With 2 grams of saturated fat per tablespoon of olive oil, the average separation time was 41.612 seconds. Sunflower oil had 1.5 grams of saturated fat per tablespoon, and its average separation time was 45.234 seconds. Canola oil had the lowest concentration of saturated fat, with 1 gram per tablespoon, and its average separation time was 79.344 seconds. These results showed that it took more time for the canola oil to separate, which had the least amount of saturated fat, while it took the least amount of time for the olive oil to separate, which had the most amount of saturated fat. Throughout the experiment, there didn't seem to be any outside factors that could have affected or influenced the results from the trials. The data collected seemed to be precise and accurate, and also identified with the background research that was done. This experiment was fairly simple and no mistakes were made in the process, so no major changes are necessary to the procedure.
So our presentation is about, does the substance inside a water balloon affect the speed that the water balloon pops when popped by a needle? So our question was, does the density of a liquid substance within the balloon affect that speed at which it pops? And it's important because density is something that affects everything. Finding out whether density affects speed will connect to many real-world things. For example, the density of Dead Sea in Jordan is higher than most other seas, and that affects swimming and people in the water.
Or abstract. This experiment was designed to test the relationship between density and speed by changing the substance inside of a standard water balloon. It is hypothesized that the substance inside of a water balloon would affect the speed that a water balloon pops when popped by a needle. This hypothesis pivots on changing the substance inside of a water balloon with various liquids at different densities. Using a slow motion camera and a controlled setup, the data was recorded on every balloon when it popped. Through calculating the speed using the slow motion footage and the tools on the footage software, it was concluded that the density of a substance does not have a direct effect on the speed of the pop. The hypothesis was proven incorrect by the experiment and the data. Oh, just again, our hypothesis to restate. It was hypothesized that the substance inside of a water balloon would affect the speed that a water balloon pops when popped by a needle. And our variables, our independent variable was the liquid substance within the balloon. A constant variable was the amount of liquid in the balloon, which was just 50 milliliters. And the dependent variable was the speed at which the balloon pops.
All right, so getting into our research, we had theory and background information. The purpose for this experiment is to find out whether density has an effect on the speed in the contents of a water balloon. There are many examples of density's effect on speed in the world. One example would be helium balloons. Helium balloons rise because helium is less dense than the surrounding air. Over time, the helium escapes the balloon and is replaced by air, causing it to sink. This shows that density has an effect on how a balloon moves and acts. It's hypothesized that when the balloon filled with substances of varying densities, it would affect the speed that the balloon pops at. The relationship between density and speed is used to back up our hypothesis. Another real-world example of this relationship would be density's effect on the speed of sound. In an article about the speed of sound, it stated, the speed of sound in a solid depends on the Young modulus of the medium and the density. Density is a variable that has an effect on speed. A table with measurements was given as proof. Ethanol has a lower density than water, making the speed of sound faster. The greater the density of a medium, the slower the speed of sound. It is believed that in the balloon substance density experiment, similar results would be seen on the way density affects speed. The comparison gives an idea on a few things that could have an effect on the final result. In the speed of sound data, there are many variables that had an effect on the final speed. This could be true for the balloon density experiment as well.
In our research and application, so the data application for the balloon density experiment relies on the relationship between density and speed. The reason it applies is because the speed of sound can be altered by changing the density of a medium, and it's hypothesized that the same is true for a water balloon. An article states, sound waves are made up of kinetic energy. It takes more energy to make large molecules vibrate than it does to make smaller molecules vibrate. Thus, sound will travel at a slower rate in more dense object if they have the same elastic properties. If sound waves were passed through two materials with approximately the same elastic properties, such as aluminum and gold, sound will travel about twice as fast in the aluminum than the gold. This is because the aluminum has a density of 2.7 grams per cubic centimeter, which is less than the density of gold, which is about 19 grams per cubic centimeter. In the experiment, the medium inside of the water balloon will be changed. Each medium has a different density. If the experiment is similar to the speed of sound, the less dense medium should pop faster than the more dense ones. And our procedure summary. For this experiment, it was ensured that there were 25 water balloons from the same company, made from the same material to leave as little room for error as possible. Next, we set up a slow motion camera and lights with the help of an expert. This process was done in a professional office. Next, each water balloon was set up on a holder to ensure that the needle would strike the same area every time. Then the balloons popped. The slow motion camera pinpointed the exact moment where the balloon pops, and the distance it traveled can be calculated using the software on a computer. This software helps calculate the measurements needed to find the speed of how fast the balloons popped. After the camera was all set up, 5 water balloons were filled up with isopropyl alcohol, vegetable oil, water, corn syrup, and Elmer's glue. Each balloon was filled with 50 milliliters of the substance. Then, all 25 water balloons were popped and the data was recorded. The camera processes all of the data for each shot, so the distance and time can be found to calculate the speed. Once the time and distance are found using the computer software, the numbers are plugged into an equation for speed. The final step is just to compare all the results and see if the hypothesis is proven correct.
So the next is data collection, and this is kind of how we got the numbers for the data. So the distance calculation. There needed to be a precise way of measuring the distance of the pop in the balloon. In order to find the speed of an object moving at such extreme speeds, something on the screen must be measured that has a known distance. In this case, the diameter of a wooden stick was measured at 3 millimeters. 3 millimeters was then put into the computer software and calculated the distance per pixel. For this experiment, the number was 0.12 pixels per millimeter, millimeter. This number was used to find the distance in millimeters with a red line on the screen. And to calculate speed, speed was a very crucial calculation for this experiment. The equation for speed is speed equals distance over time. The footage was recorded at 50,000 frames a second, so 10 frames were used as a number for the time calculation. 10 frames at 50,000 frames a second is 0.0002 seconds. When the tear of the balloon first started, a green mark was placed, as you can see on the left in the picture. Next, 10 frames were counted, and a second marking was placed on the end of the tear. You can also see that in the left of the picture. The red line gives the distance, which will then be divided by the time, which is 0.0002 for each trial. This gives us a speed in millimeters per second. Divide that by 1,000 to get the speed in meters per second, which is much more commonly used. You can see the equation down below for speed. And this is we have one example for water trial 1, and this is just how it looked. Corn syrup. And then we have a chart showing all of that, and the purple is the average in meters per second. And we have a discussion. So the data showed that the density does not have a direct correlation with the speed at which a water balloon pops. It was hypothesized that the higher the density of a liquid inside a water balloon, the slower the speed of the pop should be. However, the data does not seem to support this hypothesis. The data showcases that some of the trials followed the hypothesis. For example, corn syrup had a much lower speed than the water did. Corn syrup has a density of 1.4 grams per milliliter squared, whereas water is only 1. This goes along with the hypothesis and is what is predicted to happen during the experiment. Isopropyl alcohol, however, is less dense than water but had a slower speed. The density for alcohol was 0.79 compared to water, which is 1. This goes against what is hypothesized and shows that the relationship between density and speed may not be what is expected. The same is true for vegetable oil trials, but they were much slower than water, even though vegetable oil's density was only 0.01 grams per milliliter squared lower than water. This harsh change may be likely the result of something different than just the density alone. Glue also goes along with the hypothesis, showing that it is slower than water and faster than corn syrup. This was predicted because glue's density was in the middle of the two. Overall, there's not enough proof to support our hypothesis, but it's evident that density has something to do with the speed.
So, our errors. In this experiment, there was much room for error within some variables and could cause some inconsistency in the data collection. One of these miscalculations could be the accoutrements used, specifically the speed of the angle at which the needle was when the balloon was popping. The needle was thrusted into the balloon manually. Because of this, it was impossible to ensure that the balloon would be hit and popped at the same spot and at the same speed consistently. Another error unaccounted for could be the substance's reaction to latex, the substance the balloons were made from. It was believed that vegetable oil does not react to latex well, causing the results of the vegetable oil to be misleading. The vegetable oil popped much slower than expected, leading this belief. Henceforth, the hypothesis may be deemed invalid or incohesive and should not be taken as fact. In the conclusion, this experiment done has proved that density of a liquid substance does not affect the speed at which it moves. Density is crucial in figuring out many things. The information found is very relevant because density includes what substances are capable of allowing different items and substances to float or sink. For instance, the density of the Dead Sea in Jordan is higher than most other seas, and that affects swimming and the people in the water. Density could very well be what leads society to many important discoveries in the near future and should definitely not be overlooked.
And that's our works cited.
How does an aerogel composite sheet insulate compared to other common materials? By Colby Godwin
and Simon Wabner.
So for the abstract, in this experiment, 4 plywood boxes are created and the temperatures of the boxes are measured over 15 minutes in the freezer. The boxes each have different insulation material on the inside, those being no insulation, spray foam insulation, fiberglass, and an aerogel composite sheet. Aerogel is the world's lightest solid and a really effective insulator, being comprised of anywhere between 95 to 99.9% air. The idea is to see how well the aerogel will insulate the air inside the box compared to the other generic materials. It is hypothesized that the box containing the aerogel will insulate the box at least 1.5 times more efficiently than the other boxes.
So for the introduction, the question is, how much better is aerogel at insulating than other commonly used materials? The purpose of testing the different types of insulation is so that one can find if aerogel insulation is more efficient. It would help homeowners save money, and at the same time, it would reduce the need to heat/cool houses as much, which would be good for the environment. So we hypothesized that aerogel will insulate 1.5 times better than other commonly used insulation materials and will therefore keep the temperature of the inside air warm for much longer than the other boxes.
So for the background information, aerogel is an interesting material that has been recently discovered. It's made up from anywhere between 95 to 99.9% air. And since air is a great insulator, aerogel will be too. Besides air, aerogel is also made up of silica that is combined with a solvent. And then this solvent is extracted through a pretty complicated process. And that's how you get aerogel. Since aerogel is a relatively new discovery, the production rate is very slow and it's pretty expensive. This experiment uses a composite sheet of aerogel made up of 70% aerogel, 15% fiberglass, and 15% polyester. This won't be as effective as pure aerogel, but it will be more cost efficient while still providing great insulation. Pure aerogel would be over 2 times as good as an insulator as fiberglass and spray foam with a specific heat capacity of 2.1 joules per gram degrees Celsius. For comparison, standard fiberglass insulation has a specific heat capacity of 0.88 joules per gram degrees Celsius, and spray foam has one of 0.98 joules per gram degrees Celsius. The price of the composite sheet is $4.89 per square foot, and the price of good fiberglass is about $2.40 per square foot. So the aerogel is a little bit more than twice as expensive, but it's also a little more than twice as effective at insulating. Using this knowledge of the high specific heat capacity, the experiment was designed to test how good aerogel is at insulating objects in comparison to the most generic insulators. To test how good the insulation is, the experiment with great contrast and temperature to show how well the aerogel will keep the inside of the box warm as opposed to the other groups. And specific heat capacity. Specific heat capacity is the amount of heat required to raise the temperature of an object by 1 degree. The equation to calculate specific heat capacity is C equals Q divided by M delta T, where C is the specific heat capacity, Q is the amount of heat applied in joules, M is the mass in grams, and delta T is the change in temperature. This is derived from the equation Q equals MC delta T, where the specific heat capacity directly correlates with the amount of energy applied. This means that an object with a higher specific heat capacity requires more energy to change the temperature, thus making it a better insulator. The units for specific heat capacity are joules per gram degrees Celsius, with G being 1 gram of the material. And thermal conduction is one of the 3 ways to transfer thermal energy. Conduction works when 2 objects with different thermal energies come into direct contact with one another. The thermal energy is transferred between the 2 objects until they are both equal. The model below shows 2 objects of different temperatures that come into contact. The energy is dispersed evenly throughout both objects until they have the same thermal energy.
So materials. The necessary tools/materials include a jigsaw, wood glue, plywood, spray foam, an aerogel composite, fiberglass insulation, a freezer, a lab quest, a temperature probe, a ruler, a drill, a 3mm drill bit, and scissors. So for the procedure, start off by making 4 plywood boxes with dimensions of 5.08 centimeters by 10.16 centimeters by 6.35 centimeters. Leave off the top of 3 of the boxes, and the rest of the boxes should be held together with wood glue. Fill the 3 boxes with an aerogel composite, spray foam, and fiberglass. The insulation should be attached with wood glue and should be 15 millimeters thick on each wall of the boxes. Glue on the tops of the remaining 3 boxes. Drill a 3mm hole into each of the boxes. Leave the boxes in a room temperature environment for 24 hours. Put the boxes into a freezer that should be about -5 degrees Celsius for 15 minutes each, measuring the temperature inside of them using a lab quest with a temperature probe. So model of the experiment. In this model of the experiment, you can see a 3D model of one of the boxes. On the left side, there is insulation, and on the right side, there is no insulation. The green dots inside represent the room temperature air particles. The arrows represent the outside air transferring thermal energy into the box through conduction. The outside air on the left will have a harder time transferring heat because there is more material between the outside and the inside air, and the high specific heat capacity of the insulation will require more energy to have a change in the temperature. The outside air on the right will have a much easier time conducting through only the wood, thus making it a quicker process to lower the temperature of the air inside. So here are some of the procedure photos. You can see how they're all photos done in the freezer, and the boxes connected to the lab quest, which is like the gray and blue computer, and there's sticky notes to label which insulation is in which box.
So for our results, and this is the table of trial 1, and you can see at the top, those are the types of insulation, and on the left, that's the time in minutes. On the left side, you can see the time elapsed in the freezer in minutes. It goes from 0 to 15. And on the right side, those are the temperatures in degrees Celsius. So this is the same for trial 2, same for trial 3. And for the averages of the trials, we took the averages of trials 1, 2, and 3, and we put them all together into one table. And we used those averages to make a graph, and this graph shows the averages of the temperatures of the boxes when put into the freezer. And the y-intercept shows how each of the boxes started at room temperature, and over time, each of the boxes' temperatures decreased more and more, with the no insulation dropping the most. So for the discussion, after 3 trials were done for each type of box, data was collected and plugged into the tables. The average was then found of each insulation type at every minute. A table was then created with all of the averages, which was transferred into a line graph. The line graph shows how well each box held up on average over 15 minutes. On average over the 15 minutes, the no insulation box went down by 16.3 degrees Celsius, the spray foam went down by 10.4 degrees Celsius, the fiberglass went down by 7.9 degrees Celsius, and the aerogel sheet went down by 4.5 degrees Celsius. The aerogel was about 1.75 times better at insulating than the spray foam and 2.3 times better than the fiberglass, proving the hypothesis to be correct. These numbers also line up with the specific heat capacities given, being 2.1 joules per gram degree Celsius for aerogel, 0.88 joules per gram degree Celsius for fiberglass, and 0.98 joules per gram degree Celsius for spray foam. Although the hypothesis was proved to be correct, there is still room for error in the process.
Some sources of errors for this experiment could have been the boxes not having the exact same dimensions. They could have been a couple of millimeters off due to the saw not being exactly precise. Another possible source of error could have been the varying amounts of wood glue that was used to make the boxes. If slightly more wood glue was put into one of the boxes, that could have given it more insulation. Another possible source of error could have came from the temperature probe not being completely airtight in the boxes, which would have let some air in. A fourth source of error could have came from the insulation not being exactly 15 millimeters thick, which would have given a box more or less insulation.
For the conclusion, in conclusion, the aerogel composite sheet ended up insulating better than hypothesized, doing more than 2 times better than the fiberglass and costing about 2 times as much. The aerogel composite sheet proves to insulate very well. If the means of production of aerogel increases, the cost will most likely decrease, allowing it to be more easily accessible to the public. And if people are able to use insulators like aerogel in their homes, a lot of money could be potentially saved over time on heating and cooling, again, also being better for the environment.
And then these are just some of our references that we used.
How do enzymes affect the effectiveness of laundry detergent on stains? My question is, are laundry detergents with enzymes more effective than those without them, those being biological detergents? And if so, to what extent? What I seek to understand is how much more effective laundry detergents that contain enzymes are than those that don't contain them, which are often shown as biological detergents and non-biological detergents when being sold in stores. Significance is that detergency is very common internationally. It's used in all households, and understanding how detergents work can assist in saving costs, purchasing the right detergent, and generally understanding how they function in a household and increasing their efficiency overall. In my experiment, my independent variables are the types of detergent and the types of treatment in particular. The first type of treatment is biological treatment, non-biological treatment, and distilled water. The biological treatment is the enzyme-containing detergent, and the non-biological treatment is the non-enzyme containing detergent, and then distilled water is distilled water. The dependent variables are the intensity of, which is the brightness of the stain following the treatment. My positive control is a lack of treatment to the stain on its own, and my negative control is the detergent/liquid treatment. My hypothesis is that biological detergent, which contains enzymes, will be distinctly more effective at removing stains than non-biological detergents. This is because biological detergents, in addition to surfactants and alkalis, also uses enzymes like protease, amylase, and lipase, which can assist in and accelerate the breakdown of proteins, stains, which are starch-derived, in lipids in a fabric that have become the stain, rather than simply using surfactants and alkalis to try to use emulsion to remove the stain. That is going to be explained here. Surfactants are molecules that derive from fats. They contain a polar head and a nonpolar hydrocarbon tail. A very common example of a surfactant is soap, which is pictured below here. When surfactants saturate the surface of water, excess surfactant molecules, when they fill up the surface, form these things called micelles, which are polymolecular aggregates that can trap nonpolar stains inside it. And then when rinsed out with water, those micelles are removed, thus removing the nonpolar stain molecules inside. This could be things like oils and all of the examples that are shown in the stains that we'll have later in the experiment. Effectively, it's because of this hydrophilic head and hydrophobic tail that they form these micelles, where the hydrophobic tails don't want to interact with the liquid around it, specifically the water, and as a result, they'll form those ball aggregates that can trap stains inside. The other part of surfactants are alkalis, which are soluble salts in a base. What they do is they react with an acid, neutralizing it in the liquid, and then these salts form an emulsion through their solubility in water. And then oily and solid particles are then held in suspension within wash water and can thus be rinsed away very easily. It's similar to what was shown before with emulsion. This specifically occurs, the neutralization occurs with hydroxide being dispersed in the water from the alkalis and soluble salts. Additionally, emulsifiers exist when alkalis interact with surfactants, and that allows micelles to be produced in both cases. Micelles being those aggregate balls. And laundry detergents, the ones that are biological, they include enzymes as well. So for example, protein stain enzymes use proteases to be broken down. Amylase is another enzyme. This breaks down starch-containing strains. And lipase is another enzyme that hydrolyze triglycerides, which are going to be those oils and those lipids, and can break those down as well. The general chemistry behind it is you have a enzyme, and the enzyme attaches with a substrate that catalyzes, which means accelerates and allows a reaction to start, which can break up the substrate. The procedure is pretty simple. At the top, we have our materials. I cut 12 5 by 5 centimeter cotton squares and arrange them into 3 columns of 4. 3 jars are then filled, one with 250 milliliters of distilled water, one with 250 milliliters of non-biological liquid detergent, and one with the same amount of biological liquid detergent. Each of the squares per column is then placed within one of the solutions, shaken within the jar for 1 minute, and then removed, rinsed, and dried. I then use a software called ImageJ to measure the intensity, which is the brightness of the stain, after completing the experiment. I then create histograms to be further translated into a graph. Measurements must be taken in equal size across samples and in a consistent and maintained region of thickness for accurate results. So this is my first set of data. In figure 1, we have the images used in the image analysis software. Pictured on the left is our mustard stain, in the center is the egg yolk stain, and to the right is our oil stain. From the top, we have our control, which is our untreated stain on its own. And then to the bottom left, to the bottom right, we have the distilled water treatment, the non-biological treatment, and the biological treatment, each to varying effects. I then put this into the ImageJ software and produced histograms in figure 2. So these histograms use something called the mean gray value. What the mean gray value essentially is an average brightness and intensity in the region selected for the stain. As the mean gray value goes up, that can signify a decrease in the intensity of the stain as the fabric behind it begins to become more visible. This will then be extrapolated into a graph later, but this shows the general data. At the bottom, we have the minimum value, the maximum value, as well as the mode. We have the count, which acts as the general size. Because this is an image, it's related to pixels. And the mean would be the average gray value, which is what is used in the graphs. So pictured here is the egg stain, pictured on the right is the mustard stain, and pictured here is the oil stain. As for the graph data, taking the mean gray values of each, we can see an upward trend in the mean gray values as we increase in the treatments, which shows a maintained upward increase in a maintained trend in the decrease of the stain intensity itself, which means that as we move from the control to the water to the non-biological to the biological, we see a maintained increase in the deterioration of the intensity of the stain. It is most evident with mustard stain removal, as well as with egg stain removal, where for egg stains, it's a bit less intense. In this figure 3, once again, we can see there's a upward trend in all of them. Specifically with egg stains, we see a smaller difference between non-biological and biological, as well as with oil stains, whereas this is the smallest. But in mustard stains, we see a distinct increase. Additionally, the actual y-axis, which is the range and intensity mean gray value, goes all the way from 0 to 255, which relates to the range in mean gray value in an 8-bit image. If we go back, we can see that once again in the histograms. So our conclusion is that the data shown matched our hypothesis overall and confirmed it. The intensity of the stain decreased as the treatment went from distilled water to biological over the short period of time. The mean gray value increased with each treatment, signifying that the stain was fading into the white fabric below. By confirming our hypothesis, we can conclude that biological detergent is in fact more effective than non-biological detergent, but not by an overwhelming margin. The extrapolated data can also inference that enzymes likely accelerate the speed and efficiency of stain removal when acting alongside surfactants and alkali. Thank you.
This investigation was completed to determine the effect of temperature on the intonation of instruments. The question was, how do changes in temperature affect the intonation of instruments? Does it affect woodwind and brass instruments differently? And can plastic cover reeds help combat changes in pitch that may occur? So this is important because musicians face issues when playing outdoors, especially in extreme temperatures. It's generally a lot harder to play in tune. This happens a lot, especially with marching band practices and at football games. So the goal is to find out which temperatures make the pitch go up and which ones make it go down, so that when playing outdoors, players can adjust the instruments accordingly and play in tune. Being in tune is very important, and being in tune can enhance performance. So the constant variable is the note being played, the control is the room temperature, and the dependent is the frequency of the note, and the independent variable is the temperature of the room. So for the hypothesis, it was hypothesized that colder temperatures will lower the pitch and hotter temperatures will make the pitch higher in both wood and brass instruments. It was also assumed that using plastic cover reeds on clarinet will help keep the instrument in tune because it will keep the reed from drying out and being warped in the changed temperatures. So the main points that are relevant to the experiment are how sound waves work and how wind instruments make sound. So sound waves are created by an object vibrating, causing the surrounding air molecules to vibrate and set off a chain reaction that eventually reaches human ears. And so frequency is the number of vibrations per second, and so a lower frequency produces a lower sound, and a higher frequency produces a higher sound. Another important factor is how the instruments make the sound, and so with a clarinet, the reed is important. The reed is a piece of wood on the mouthpiece that vibrates in order to produce the noise. And on the trombone, instead of a reed, it's the player's lips that vibrate and produce the noise. So Gay-Lussac's law states that as the temperature goes up, the pressure also goes up, and that the pressure varies directly with the temperature. So when the temperature decreases, the particles of the gas slow down, so there are fewer collisions between the particles and then the particles in the side of the container that they would be in. So overall, when the temperature decreases, there's less molecule movement, and the opposite happens when the temperature increases. So from the background research, the way that it connects to the hypothesis is that the two factors that could cause the pitch to change is the air molecule movement and the clarinet reed vibrating differently due to the temperature changes. It's possible that it was speculated that the reed might vibrate slower in the colder temperatures, which would cause the frequency to decrease. So for the experiment, 3 different rooms were created. One was room temperature, one was cold, and one was hot. In each room, the temperature was taken and a B flat was played with the clarinet and a trombone. After playing them adjust to the temperature for 30 minutes, the frequency of the B flat was recorded using a phone app, and then the whole process with the 3 rooms was recreated with the clarinet with plastic cover reeds instead of regular reeds. And so plastic cover reeds are reeds that have a layer of plastic over them in order to resist changes in the environment so that it's easier to play outdoors. So this is the data. This table shows the temperature and the frequency produced with all 3 categories, clarinet with regular reeds, trombone, and clarinet with plastic cover reeds, over the course of 5 trials. And this graph shows the points on the table. As you can see, there is a trend in which as temperature increases, the frequency also increases, which matches the hypothesis. So why does this happen? When the temperature decreases, the air pressure decreases, so there's less movement overall, and the movement of the molecules is very important with the sound waves, because the sound wave is created by the molecules vibrating, and so the frequency is the speed at which they vibrate. And so it's the conclusion was made that the slower air molecule movement caused the frequency to decrease, and then the opposite happened with the warmer temperatures. And so plastic cover reeds did not prevent pitch changes. So one observation that was recorded was that it was easier to produce a sound with the plastic cover reeds than the regular reeds in the cold and hot temperatures, which indicates the same as it would at room temperature. So since it was affected just as much, the plastic cover reeds were affected just as much as the regular reeds in the trombone. So this indicates that the pitch change was only caused by air molecule movement, because if it was vibrating the same as it would at room temperature, and it still became flat and sharp. So another point was that if the reed was a factor, then the clarinet would have been affected more than the trombone, since it would have had two factors acting on it, both the air molecules in the cold room, the air molecules slowing, and the reed vibrating slower. But instead, it ended up being affected about the same as the trombone. And since the trombone doesn't have a reed, it only had the one factor acting on it. So since they were affected the same amount, then that indicates that there was just one thing acting on it. And it was the same thing, which is the air molecule movement. So all experiments have their limitations. So with this one, it was the temperatures produced for the experiment were dependent on the weather. So as the trials went on, the weather outside became warmer and warmer. And so the cold environment ended up the colder temperatures weren't able to be achieved. And so it was always slightly warmer. However, this did sort of provide an advantage because it allowed for the collection of a greater variety of data points. And it's also possible that there were equipment errors. The thermometer might have been slightly off, and it could have given inaccurate readings. And the tuner app might not have been properly calibrated, since there wasn't a way to check the software. So overall, what has been learned from this is that when it's colder, the pitch will decrease, and when it's hotter, the pitch will increase. And this information can be used to help musicians better play in tune in extreme temperatures.